Yeah, you can share it, Radhakrishna, and we'll start in a minute or so. Once few more attendees join, we can start that. Yeah, so it will be by Tetina Petkova from Q Control is the organization, and she will be sharing. So I'll just introduce her, and then Dr. Anindita Banerjee, who is the author of the book, also she is also joining a little late. So we'll have the main lecture from 2:30. So meanwhile, we will complete this presentation that is going on, and then meanwhile we will look at the things that we'll have to start the lecture at 2:30. We'll start uh, at that time. So we'll just wait for 1 or 2 more minutes, and later we will continue with the lecture. So just give me 1 or 2 minutes. Yeah, we will look at the video first based on how Opal has or Q Control has modified Qiskit to run some of the content. So the language is in slightly, very fast English. So kindly bear with us. We'll anyway share the video with you. So at that time you can again, anyway, it will also be in YouTube, right? Thank you so much. Yeah, Radhakrishna, you can play. Make
Hello,
it full
and
screen.
welcome to this introduction of Q-Control FireOpal Qiskit functions on IBM Quantum. My name is Tatiana. I'm a product manager here at Q-Control, and I'll be joined by my colleague Yuklan, who will run the demo of how to get started working with our functions after a brief overview of the product. First, a bit about our company, Q-Control. We build software infrastructure to make quantum computers useful. Our technology sits on top of underlying hardware platforms and transforms the performance, reliability, and overall utility of quantum computers and quantum sensors by solving the hardest problems in the field. Quantum hardware today faces an immense challenge, namely that quantum computers are inherently very sensitive to interference from the environment, often referred to as noise, making them highly susceptible to error. And this challenge is amplified at scale. The bigger the problem being solved, the more qubits, the more gates, the more system will be subjected to noise. For example, a simple Grover search, a typical quantum algorithm for searching in an unsorted database or finding a needle in a haystack. The figure at the top here shows the ideal result on a simulator. And below it, you can see the result from running on bare infrastructure of a real quantum device. It is so noisy, as you can see, that the correct answer is completely obscured. So while Grover's search is mathematically proven, it is very difficult to implement in practice. This experience affects overall perception on the usability of quantum computers in general, and it is extremely disheartening and frustrating for application developers. Addressing specific types of errors requires a high level of hardware-specific knowledge and implementation. But overcoming these challenges is increasingly critical as quantum computing hardware and application development continue to advance. So whether you're modeling molecular structures, solving optimization problems, or estimating ground state energies, your approach to error reduction can significantly impact your results. FireOpal is our answer to these problems. It allows you to run valuable quantum applications without experiencing all these errors and noise. It automatically suppresses errors on the device to enable the circuit to run optimally and just return quality results upon execution the first time. It is very easy to use, an out-of-the-box solution that does not require hardware knowledge and works across any algorithm and application. This allows developers to expand to more complex, interesting use cases and run circuits at the scales of over 100 qubits or thousands of gates. Our performance management software was first natively integrated into IBM Quantum Services in 2023. The following year, we launched our Qiskit functions as the next evolution of native integration for achieving utility scale. Qiskit functions expose both of our main FireOpal features: performance management, including our core error suppression, and our solver, which takes optimization problems such as vehicle routing, scheduling, portfolio optimization, and tackles them. Let's zoom in on performance management. How does it work? At a high level, it abstracts hardware the same way that classical computers abstract assembly level language, memory, or classical registers. The underlying technology is autonomous and invisible to the end user, enabling them to focus on their algorithms while obtaining maximum achievable performance from the hardware devices. So the developer is simply sending in a high-level quantum algorithm, executing using the performance management function in a single line of code, and receiving a performance-enhanced answer without having to worry about the rest of the software or hardware stack. In this case, that hardware would be IBM. To get a little more in depth on error suppression, a circuit and parameters or observables are given as the input. The function has two primitives, sampler and estimator, and the inputs and outputs of both extend the implemented spec for Qiskit runtime v2 primitives. More on this in our demo. The fully automated error suppression pipeline then reduces errors by altering the circuit at the gate and pulse level and utilizing a combination of techniques to address different sources of noise. The user doesn't have to worry about depth reduction, hardware mapping, etc. They just submit their circuit, which we pre-process, run on the quantum device, in this case IBM, and then return optimized results. By aggressively compiling the circuit and reducing the overall depth of the initial circuit that is inputted, as I just mentioned, we enable users to run circuits that are 10 times deeper, meaning 10 times more 2-qubit gates. This also enables us to return the right answer in less runtime, because increasing accuracy means we don't need to run as many shots. So not only are we getting the right answer, but we are getting it in less time and with fewer compute resources and overhead. As an additional note, this is particularly helpful for iterative algorithms where we can reach convergence much faster, saving overall on additional runs. Everything we do is deterministic as well, meaning there's one output for a particular input. And all of this is far more efficient than, for example, error mitigation, which requires extensive post-processing and compute. To illustrate these benefits, here's a real-world example by Mitsubishi Chemical, SoftBank, and other collaborators, in which they run quantum phase estimation, a type of circuit that's really deep and expands quite quickly in terms of the number of 2-qubit gates. Mitsubishi transpiled the circuit using IBM's highest level of transpilation, and they still had over 7,000 2-qubit gates, which would go far beyond the limits of today's hardware. By using fire-opal transpilation technique, that number was reduced down to 794 2-qubit gates, so an order of magnitude less, enabling that circuit to be successfully runnable on today's hardware. This further enabled Mitsubishi to achieve 5 times larger of a demonstration than any other previously published example of quantum phase estimation. With our technology, we really strive to enable users to push the boundaries of what's possible for real-world applications. And there are many other examples of successful quantum applications happening today, ranging from QML to quantum data quantum data loading, to drug discovery, all leveraging our error suppression. Ultimately, each of these brings us closer to the goal of quantum advantage. Now let's briefly talk about the solver Qiskit function before we switch over to the demo. This function is a fully automated optimization solver that accurately solves tough optimization problems at full device scale, meaning using all available qubits. The user submits a problem specification input, which is then compiled, and we then take a hybrid quantum classical execution approach, the quantum part of which leverages our error suppression that we previously described, before returning the solution. Once again, using this function is a matter of a couple lines of code, abstracting all this computational detail. And this function is already solving real-world problems. It's optimizing schedules of trains across the nationwide UK railway network. It's optimizing the routing of 5,000 convoys as part of a massive joint exercise between the US and Australian Army. It's optimizing traffic and placement of EV charging stations for sustainability initiatives. And it's also optimizing supply chain operations for aviation and automotive. So now we're going to move into the demo. Yuquan will walk you through the examples captured in the IBM catalog articles. They're in the journals that are provided there for our performance management function, including the estimator and sampler primitives, and our optimization solver function.
Okay, hi everyone. My name is Yuquan, and I would like to present to you the Q-control fire-opal on IBM Quantum. All right. And so first, what we have is assuming that you have your IBM Quantum platform API key. You can simply select the Qiskit functions as follows. So here, what we're going to select is the Q-control performance management Qiskit function. So let's try running this. And under the Q-control performance management function, there's actually 2 primitives. One is the estimator primitive, and the other one is the sampler primitive. As you see later, the estimator primitive allows for running of against observables, and the sampler primitive allows for running the simple circuits. So let's look at the estimator primitive. So what we have is that we can determine the expectation value of a single circuit observable pair. So first, let's try to create a circuit. All right, so here we're just creating a random Hermitian circuit with some observables that is all these across all the 50 qubits that we have. All right, and from this we create the circuit observable pair as a pub, as which is defined by the Qiskit interface. And what we can do is to run this against the Q-control performance management estimator. So we just need to do a dot run here, and then we just specify the primitive to be the estimator, and then we pass in the pubs to be the estimator pubs, which we defined earlier, and then you can pass in your instance if necessary, and the backend name that you like to run on. All right. And so with that, for consideration of time, we will not be running this here, but once you execute it, you can check the status, you can check the result, and then when you run this, the result will be something like this. So you'll see that there's a primitive result with the expectation value and the standard deviation, and yeah, that's it for the estimator. And for the sampler, what we can do is to run basically any type of circuits. The Q-control variable sampler, what we'll do is that we will optimize the circuits for you, and we will do error suppression and error mitigation for you. So let's look at what happens here. So basically what we'll do is to create a Bernstein-Bazzirani circuit, a very common circuit in quantum computing using 35 qubits. And the hidden string here is just a list of all ones. And at the end of the day, what we'll do is to create a sampler pub, which is a simple Bernstein-Bazzirani circuit. And then we can run the circuit again using the performance management Qiskit function with a dot run, and using the primitive as the sampler, using the pubs as the pubs we created above, and the instance as your IBM instance, and the backend name could be IBM Fast, IBM Marrakesh, or whichever backends that you have access to. And then for the sake of time, this is run here as well. But when you run it, you can grab the status, you can grab the result, and if you pull the results using get counts, as you see here, what we can do is to try to plot it. So let's try and let's first define the plotting function, and then after which, let's try and see if we can plot the results. And yes, so we have the results, and you can see that the top bit string here, which is highlighted in purple, is the bit string that we that is also the hidden bit string of all ones as expected. And the rest of the probabilities that are not the top bit string or the expected bit string, these decay with exponential probability. Yeah. So here we have a demonstration of how the sampler and the estimator works for the Q-control variable on IBM Qiskit functions. And I'd like to give a walkthrough for the Q-control optimization solver on Qiskit functions. So first, let's get started. We can first authenticate using your IBM Quantum API token. And once that is done, you can access the Qiskit function as below. So we can simply get the catalog and load the Q-control optimization solver using the catalog. In the Q-control optimization solver, it mainly works through the types of problems that are using a classical quantum iterative algorithm called the QAOA. And in this example, we'll look at an unconstrained optimization on a max cut problem. So for optimization here, what we are going to do is to address a maximum cut problem, which is, let's say if we are given a graph, how do we split it into two subgraphs such that the number of edges in that is cut is maximized. All right, so this is an amply complete problem, and we can define the problem as below. So first, we can, let's say, create a random graph with 156 nodes here, and we can simply visualize it. And as you can see, this is a very complicated graph with 156 nodes. Each of them has, we defined it to be d equals 3. So that is a 3 regular graph. So each of these nodes have 3 edges coming out. All right. And for it to work on the Qiskit functions, we need to pass in the input as a string. So let's do that. And for the sake of time, we will not be running this problem. But if you want, you can try passing in to the solver using the .run. Firstly, passing in the problem as a string. Secondly, the problem type as max cut, and then your IBM instance and your desired backend name. And if you run this, you can again grab the status, and after about waiting through the whole run, you should be able to grab the result and the solution bitstring cost here. So in this case, the optimal cut value of that graph is 157 here. All right, thank you.
So that was our demo featuring the example problems from the IBM catalog. The notebooks can be downloaded from there. And thank you. You can utilize this QR code to easily request access to Qiskit functions, the functions that we went over today. Please note that IBM Premium Access is required to use these functions. And we hope this presentation was helpful and are excited to see all the new ways that you'll apply this technology.
Yeah, thank you so much. Hope you would understand what they actually were speaking. It was an extension to Qiskit, which they have developed and where they have used it for other companies. So the QCTRL modified a certain code of Qiskit and used it. So they are giving you access. So if you would like to go through that, and you can use the QR code that was shown. If you go back to the video anyway will share in the modules, this thing, it will be available. YouTube link is anyway there, both we will share. So you can look at the QR code, scan it, and get access to the Qiskit functions which they have modified, and you can use that. So that is the thing. Yeah. Q control does a lot of things for, in fact, but they are more into training and research. So they have actually approached us to make a training demonstration. So I requested them to do a technology presentation. So that's where it's this thing. So they mostly work only with this Opal framework. So if you would like to search more into it, you can look at OPAL, Opal. Opal framework is what you can try to look at. But by and large, yes, they are into Qiskit customization, and you can use it. So that way, there are many organizations like that. So one of them is Opal, and they have an integration with Qiskit. So that's what we're trying to look at here. in another 1 or 2 minutes, we'll be joined by Dr. Anindita Banerjee. I'll quickly introduce her and then we'll go ahead with the session. So just waiting for 2 minutes, 2:30. She'll join, and maybe kindly bear with us. The session may extend a little beyond, or she may conclude by 4 o'clock because she also has a meeting. Actually, that's unfortunate. But anyway, let's hope if she's able to give the time, she will be there for 2 hours and she will work out the whole thing, right? So I will just introduce her and then we'll have the session. So once again, for those who joined late, we just had a presentation by Q Control, you can say, or QCTRL company. So yeah, the quiz 2 and quiz 3 are open, so you can take the exam. Quiz 3 exam content, some of the content is to be added. I think Anand Raman's content has come. I'll add it quickly. So I think Dr. Ritajit had an operation, so he's not able to use his eyesight. I mean, he's not able to view the screen and do something. So I think he'll send it in a day or two. That's what he told. So you can take the exam a little late, no problem. As I told you, one of the session will maybe on, instead of 5th, we may have it on 8th, that is Sunday. So so till 8th we'll keep at least till Sunday we'll keep the quiz 3 open. So you can take the quiz 3. Don't worry, don't do it now. Do it after you get the content and take the quiz. I heard that it was a little tough also, so you wait and get the content prepared and then take the exam, no problem, right? So we'll just wait. I think we're just waiting for ma'am to join. Yeah, don't worry about that. In fact, last time also we tried to help you to take 3 out of 4 quizzes. We took best 3 out of 4 to give more excellent to more participants because of the hard work that you're putting in. And thank you so much, because almost 900 people have taken quiz 1 and about 800 people have taken quiz 2. So I'm happy that we'll be issuing 900 certificates this time, and continued interest also is there. And the remaining syllabus, I'll be happy to announce that QT-05 syllabus is ready. The speakers are ready. Everything is set, and more people are interested. This time you'll have 3 IBM speakers speaking for 4 to 5 hours each. So that's very good content being covered, and we'll also have some more people are joining in, and so that way I think we are doing it. So we will try to be very positive, because we are all faculty members, and I'm hoping that, and many of you are PhD holders and professors already. It's very heartening to know many of you are elder to me also. So I think that's a very good this thing. So QT-05 content will release the folder immediately, and 6, 7, 8 are also being worked out. So mostly by July first week, we will release all the folders, and we will also share the information about the PG certificate. We are working out with the AICTE, so we are looking at, instead of MNIT giving it, we want to AICTE to give it. So it will be more authentic. You are doing the course of AICTE, and AICTE gives the certificate. We'll try to do that. So of course, MNIT, AICTE academies, and AICTE. We'll try to look at what best we can do. So hence the things are actually evolving slowly one after the other. QT-01 videos are ready. We may offer it as a course shortly. So good that already 300 people have joined. So I'll just remind ma'am once, because you can meanwhile see this. You'll be happy to see who is Dr. Anindita Banerjee. You'll be happy to know that. I'm just giving you 1 minute. Share the screen itself. Yeah, so if you're able to see this is the model curriculum for minor degree for UG degree course in quantum computing, which has this is what we are actually working on. So this was prepared by DST, National Quantum Mission, and AICT, and this is the model curriculum that we are looking at. And then these are the people who are instrumental, Professor Sitaram and Professor Abhay Karandikar. But these are the contributors which are coming up. Next slide, next page you'll see. So Dr. Arindam Ghosh from IIC and Dr. Anindita Banerjee from CDAC Pune. So she will be speaking to us, one of the authors of these whole syllabus, the committee members, the main committee. Of course, we all know Dr. L. Venkat Subramaniam, who was there from IBM, and he is helping us in many ways. And now we have Dr. Anindita Banerjee, who will be speaking to us today and also on Friday. So 4th and 6th, she will be taking the lectures. So hopefully we'll try to look at that, right? So when Madam comes back, I'll quickly introduce and hand it over to us. Give me a minute. I'll just call Ma'am and find out. Radhakrishna, can you send me the participant link?
Sir, just a minute.
Yeah. Just be on hold for a minute. Yeah. Senthil Kumar sir, actually exactly the same thing. Instead of EICT doing it, we will give the certificate from EICT. IBM is helping us to interact with them and get the things done. So hopefully we will shortly, instead of EICT issuing a certificate, we will have the AICT certificate to be done. So we'll try to do that right shortly. Yeah, ma'am is joining. Just give me a minute. There was some connection issue. Radhakrishna, can you check the registration ID of ma'am? And we can share with her so you can join fast.
Yes, sir. Okay.
You can WhatsApp me.
Okay, sir.
Participant, please be patient. Sorry for the inconvenience. Yeah, ma'am has joined, and yeah, it was a joy. It is a joy for me to welcome Dr. Nindita Banerjee, who is amongst us today. And just as I've shared you, she was one of the main, committee members who framed the syllabus for the model curriculum of minor course in quantum computing, approved by AICTE, National Quantum Mission, and Department of Science and Technology. And we are actually running those courses, so it was a joy. Recently, it was a privilege. We both were speaking in a quantum computing workshop in JNTU Kakinada, where she had shared a lot of great ideas which CDAC is implementing with the students and also in faculty development, and also building solutions which can be used for our country. So I will, and she did her PhD from JP University, Noida, and she's been a teacher earlier, but now she's joined CDAC, and she is now the technical project manager leading the quantum technology projects on aerial quantum communication, fiber quantum key distribution, quantum test center, next generation quantum computers. She was earlier scientist with CDAC India as well, in Pune, based in Pune. Before that, she was in Bangalore, part of QNew Labs Private Limited, as research head and vice president. And prior to that, she was part of the Bose Institute, Greater Kolkata, and she taught in Bengal College of Engineering and Technology for Women. And then she was a visiting scholar for University of New Brunswick, and also Institute for Quantum Information Science, University of Calgary, for 3 months. So this is the varied experience that she has, and a lot of innovative ideas which she's implementing with young people there in CDAC, and also a lot of industry initiatives and government initiatives. So it's a joy that we have one of the authors of the curriculum with us. And thank you so much, ma'am, for joining. Without wasting much time, hand over your session. You can complete your full session as much as you would like to take. So we'll be willing to listen more from you. And ma'am will again joining us on 6th on Friday. We'll be listening to ma'am again for 2 hours, where she'll be sharing a lot of challenges of quantum computing. Thank you so much. Over to you, Dr. Nindita Banerjee.
Thank you, sir. Thank you for the kind introduction. And I think again, without wasting further time, I will straight on jump to the session. So I will now be sharing my screen. Is this visible, sir?
Yes, you can. Yeah, it's fully visible.
And is this slide also moving?
Yes.
Great. Thank you.
Ma'am, one small request. Around 1 hour after you go into the session, you can, wherever you would like to give 50 minutes or 1 hour, there'll be one break. We want to change over the video. So because it's a 2-hour session, we'll make it 2 1-hour sessions, right? So just give a 5-minute break. So whenever you would like to, somebody will remind you also. And they'll be very much interactive. So you will be maybe as and when it's possible, you can look at the chat and answer the queries as and when you can, as depending on the way you schedule. Thank you so much.
Okay, sir. Okay. So I'm a little worried about the bandwidth. So I was just see if this works because I don't want to get stuck. So yeah, welcome everyone into the quantum world. So here we will explore most of the time the optics part, but also on how we are using these optics for doing quantum technology experiments. And the basic idea, as Dr. Pillai had earlier discussed, that to see how the course which has been designed based on the inputs from different technology verticals, and since we're talking about optics right now, so how these kind of phenomena, interference, diffraction, or the microscope, how does polarization come into picture, where they are used in the quantum technologies, and that will be the primary focus. It will be difficult to cover, to go in depth, but would like to give you the basic construction, the working principle, and its relevance, to familiarize you basically on these topics. Okay. So I think you must be, since it's I think on almost the end of the session of the FDP program, so you are aware. But again, it is it will be good to just touch upon in a very brief manner. A bit is nothing but a 0 or a 1. It cannot exist in both the logical states simultaneously. So it is either in a 0 state or in a logical 1 state. Now that can be represented using a physical medium. So here we represent using voltage levels for input and output. All the computations are basically on this fundamental, information unit, which is either 0 or it is 1. Now, when we move to qubit, it is the quantum analog of bit. Here, it is 0 and 1. Now, we follow the direct bracket notation. So, we put the state, these gets 1 and get 0 are the logic states. And get xi is the quantum state, which shows that it is with some probability, which is mod alpha square 0, and with some probability mod beta square 1. So it is existing in both the states simultaneously. Now, the advantage of quantum actually comes with the power of superposition. Now, entanglement again is a special case of superposition. Superposition gives rise to quantum parallelism, and that is the reason certain mathematical problems can be done exponentially faster or quadratically faster, or it consumes lesser resources. If you must have visited the quantum algorithms part, and you'll find that the quantum oracle raising lesser queries than the classical, and it is all because of this particular aspect. So it becomes very important on how we to understand this particular state, a qubit state. We will go into we'll talk about how the state is generated and what are the tests we do to validate that whether the generated quantum state can be qualified as a get xi or not. So again, so now just to visualize this state, you consider an optical gadget which is called a beam splitter. As the name suggests, it splits the beam. So if there is, suppose a beam is a collection of photons. So if we have some, say, million photons coming, then you will get half of the photons in the reflected path and half of the photons in the transmitted path, if it is a 50-50 beam splitter. So it is splitting the beam, or it is dividing the intensity of the beam. Now, what happens when one unit of energy or a single photon is interacting with a beam splitter? So the output is the state will be existing in both the paths. It will have the probabilities of its existence in both the paths, reflected and transmitted. So we have a 50-50 ideally, So here the chances of getting here is half, chance of getting in the transmitted path is half. So so these are not ket alpha, these are complex coefficients. So if you have mod alpha, which is equal to mod beta, which is equal to 1 by square root of 2. So mod square becomes half. So half the probability of the photon getting detected in logical zero state, which is represented by my reflected path, and half the probability that it will get detected in logic 1 state, which is in the transmitted path. So this is also called path superposition. Now this particular state can also be used to generate random numbers. Now random numbers would mean that you'll be generating a random binary bit stream, which is either 0 or 1, and there are some certain rules of the binary sequence. Now, when you are introducing this state, get 0 plus get 1 by square root of 2 at the input of the beam splitter, and you are collecting the measurements, of course, one entity, so you will either get a click here or in the transmitted path, and I have labeled these paths. Okay, so this is a simple experiment to show that how we visualize a quantum state, how it is existing in both the path. The paths can be the logical paths. They are two distinct separate paths, and logical zero state, just like voltage levels here, we use the reflected path as logical zero state, and transmitted path as logic 1 state. So this is known as path superposition, as the single photon is in 0 and 1 simultaneously. So this is a simple way to describe a quantum state. This can be done on the experimental test bench with a single photon source and a beam splitter. And you will see some good experiments which actually validates the results to be in the quantum regime or not through this setup. So this beam splitter is a very important quantum optical gadget. Now, I hope the previous speakers must have also discussed about the block sphere, so I will not get into the detail. It is basically a method to represent a qubit state. Qubit is a two-dimensional or two-state system. So here it is represented by transmitted and reflected, but then there are, we're not going into too much of depth. Otherwise, we have Q-trit, we have Q-dit for d-dimensional. Whenever d is equal to 2, it's a qubit, two-dimensional state. Now, what you had seen earlier was a superposition. It was a path superposition. Now, here is a class. A teacher is asking a student to give an example of the superposition after having explained this phenomena through a beam splitter. So the boy comes up with an answer of mermaid. The teacher says, well, nobody has seen a mermaid. Then the boy says that, well, it's simple, because the moment you are trying to observe the state, which is a mermaid, you're either getting, it's either getting collapsed into a fish or a girl. So that is the reason. Now, a teacher is a teacher. Now he says that, based on the, so I can, yeah, okay. So what I'm writing here is there are different bases for two-dimensional states. One is the rectilinear basis, diagonal basis. So when I'm saying logic 0 and logic 1, here it falls into computational basis states, okay? And this can also be represented by diagonal basis state, which is ket plus and ket minus. Sir, am I audible? Can you please confirm whether I'm audible or not? Yeah, okay, because I just saw that it is not audible, so I was worried. Yeah, so so now we go on to this. Yeah, so this is a so the teacher says, if the basis were mermaid itself, if the mermaid was herself another basis, and you do a measurement in that basis, then you will definitely see a mermaid. So, which he means is, if you are doing a measurement in the diagonal basis, then you will be able to observe a diagonal basis states. Now, well, when you're talking about superposition, then Schrodinger's equation is actually a linear differential equation. So superposition is inherent, but that is not the classical. This is a quantum superposition. Superposition exists in the classical world, but when I'm talking about superposition in the quantum world, it is accompanied by the wave function collapse. Okay, so just like here, the wave or the state is both at these two places, but upon measurement, it either collapses to a zero state or it collapses to a one state. Quantum gives you the probability. Okay, it will be, if there are 100 events, 50 times you will see here, 50 times you will see there. So this concept is very important. And the only thing I have introduced here is, instead of 0 and 1, ket 0, ket 1, I have introduced another basis states, another representation of this as ket plus and a ket minus. And we will call that diagonal basis states. Now, whenever you are doing any application, or you will come across this course, they will talk about cryptography, quantum key distribution, BB84 protocol. It uses 4 quantum states. 2 states from computational and 2 states from diagonal basis states. Okay, so this can be plus, this can be minus, and or a 0 and a 1. So now we will try to see, in the next few slides, we will be implementing a NOT gate. A classical NOT gate is anything which a state, and then it flips the state. If it is a logic 0, it will make it 1, and vice versa. And when you try to visualize a NOT gate, it can be done through a transistor in a breadboard. But when you're talking about a quantum hardware, we know that there are different types of quantum hardware. You can visualize it through photons, through superconducting qubits, through ion trap. There are different ways, and there are still more coming up. We never know which one is going to be taken up as a scalable quantum computer. But we definitely know that this thing works theoretically, and we have to find an efficient quantum hardware. At the moment, we'll talk about the polarizations of light. So a photon has different degrees of freedom. For example, path, polarization, orbital angular momentum, phase. So these are the different properties. While computation here and in communication, I'll be using a polarized light. In my next presentation on Friday, we'll talk about phase, because there I'm doing a terrestrial communication. Okay, so here the ket xi is represented by ket 0 state, and this is a block sphere representation. Okay, so here you will see both the four quantum states here, plus, minus, 0, 1. And let the ket 0 be represented by a horizontally polarized light. So you can visualize a polarized light like you can move one end of a string up and down. Then the wave which is created will be propagating through the z-axis, right? So if, for example, I'm talking about this, if I'm moving it up and down, it is propagating towards the z-axis, which is here it shows, right? So now you have each and every point on the string is actually perpendicular to the direction of propagation. So this is a transverse waves, and this is also a vertically polarized light. Similarly, you have a horizontally polarized light. Now, if you are applying a horizontally polarized light and you have an optical gadget, which actually changes the state of the polarization or rotates the polarization by 90 degrees, you will get a vertically polarized light. It is as if the half-wave plate is nothing but a quantum NOT gate. Now, these are experiments which can be done using a classical light also. So you have a classical vertically polarized light or a horizontally, it will flip the state. So the gadget is always a classical, but how the interaction happens, that is where the quantum comes in. So if you have a single photon, I'm using the same classical gadget to make it vertical. So this is how we will be working or operating on the single qubit states. Okay. So now we want to talk about the non-classical. I don't know if you're able to see this. So this is a non-classical light. Now this is the, okay, yeah, good, but I'm not able to hide this one. Okay, so this is a non-classical light. So what is a non-classical light? Fine. By classical light or by classical field, we mean the electromagnetic wave that is perfectly described by the Maxwell's equation. Okay, I will not don't want to get too much into it, but just want you to give you that background on why it is called non-classical. So something it is violating within which falls within the classical field, and that is the reason it has been called non-classical. And I'm sure there are my physics teachers. But I'm sorry, but you'll have to hear me again. They are familiar with this notion. So for such a classical field, the correlations between the intensity of the transmitted and the reflected light. So I'm talking with respect to this beam splitter. Okay, remember this diagram? So here it is a beam splitter. So this correlation between the transmitted and the reflected light is given by the second order temporal coherence. This is called second order temporal coherence. It is a function of time delay tau between the intensity measurements. Now we will simplify this because you have a single photon and it is existing in both the paths, and we would want to do this simultaneous measurement, intensity measurements at both these detectors. So we will take time is equals to 0, coincident, means there is no time delay. So this function is a function of the time delay between the intensity measurements. So when I'm saying tau equal to 0, it is a it is the coincidence I'm talking about. Now, I should also mention here that if the light source here is stationary, then we can interpret these brackets as the ensemble averages rather than time averages. And I should also tell you that it is called second order. Why? Because the first order is between the fields and the second order is between the intensities. Okay, so when time is equals to 0, the intensity measurements, and we are considering a beam splitter, it is represented by the intensity of the transmitted and reflected light. And it is very straightforward if you do this. Now, there is something called Cauchy-Schwarz inequality. Now, that if you again consider that inequality, then the denominator in the classical world should be less than the numerator. And what that would mean that this correlation is always greater than 1. Okay, which is the classical field. Now, so if fine, I mean, I see if we can go into the depths. I mean, we classify lights into different categories, and this is the characteristics shown by bunching property. So light actually comes together in bunches. So whenever you are having incident bunch of photons here, then you will be getting the transmitted and the they will both strike both the detectors here. So if you do this experiments, it should be with the classical light, it will be greater than 1. But if we do it with the quantum field, so it is difficult to describe it with the Maxwell's equation. In the quantum theory also, the correlations between the output fields from the beam splitters are described by the second order coherence only. But here, instead of quantum fields, the quantum field, electric fields here are treated as quantum mechanical operators and not as classical waves. Okay, and the treatment is different. And if we do this experiment, we have done this experiment in our lab as well, and we find that it is less than 0. It is less than 1. So it is violating the this inequality. Okay, so when it is violating, when the light which you are getting in lab, which through a quantum process, it is violating the inequality of the Cauchy-Schwarz, or it is the classical field, then it is termed as non-classical light. Now we'll come to this ring, how we generate this ring in the next slide. But this experiment, we have got 0.04, so it is absolutely, it is violating the classical, and it is giving me non-classical signature. So now let us understand what is the spontaneous parametric down conversion. Earlier slide, you have seen the source and it is giving out two correlated photon pairs. So here we are using a nonlinear crystal. What happens is you have a classical light, and it falls on a non-linear crystal, which is shown here with this rectangular slab. Now, upon I would say, so the length of the crystal again plays a very important role when you are actually designing this experiment. But right at the moment, let us say that it is of certain thickness. Okay, again, it comes between about, say, 3 millimeter to 5 millimeter. It depends upon the application as well. Now, and it also comes with some criteria known as phase matching condition. Okay, so now this is the energy conservation. So it requires the frequency of the signal and the idler photons is equal to the pump photon, angular frequency of the pump photon, and the momentum conservation is actually equivalent to the classical phase matching condition. And we require the wave vectors of input and output to satisfy this relation. So once we satisfy this relation, we are able to see this non-classical light coming out in a ring. Why? Because we have actually, the crystal is cut in a manner that it gives me a 5-degree from the angle from the input pump beam. That is the reason it is coming out as a cone. There are two ways, collinear and non-collinear. This is a non-collinear type of a generation. Now, this is again a type 1 down conversion, which is what we use in our experiments. I have mentioned that there is a signal and the idler beams. The polarizations of the daughter photons are each other, and polarization with respect to the pump, it will be perpendicular. The polarizations are always linear. And the reason I call it down version is because components, including the optics and the lasers, the filters, lenses, all have to cater to the different wavelengths of light. And the most important is filtering. How do I filter the light? Because the pump gives me milliwatt, which is millions of photons. And out of the millions of photons, only 1 in billion generates the daughter photons. So the task here is actually to separate the daughter photons from the mother photons pump beam, and with respect to their, as I already mentioned, that the polarization is different. So we use those things to filter out. So find the generation which I have shown here. You may question that this is a ring, but in the other slide you are seeing intersection of two rings as the generation points of the entangled photons. Well, this is type 2 SPDC, and this is type 1 SPDC. So in type 1, you will only get one ring and they are all correlated photon pairs. But here you are getting entangled photons. Entangled photons because this is the vertically polarized photons, and this ring is the horizontally polarized photons. And from their intersection comes the entangled photons. And you can see here the state is written with respect to their polarization. If you consider H as 0, V as 1, logic 0, logic 1, then the state looks like 0, 1 plus 1, 0. This is a global phase, which we can, at the moment, we don't need to consider that. And 1 by square root of 2 is nothing but my alpha and beta. They are the complex coefficients. So mod alpha square is half. So again, as I told you earlier, entanglement is a special case of superposition. So you can see the two particles coming out and they are in superposition. So it is either HV and I'm getting VH together. On measurement, the state collapses either to HV, which is also equal to 0, 1, or it becomes VH, which is also equal to 1, 0. Okay. So I hope now it is, you are now familiar with how the generation of quantum of these photons happen. So this SPDC plays a very important role in quantum optics for teleportation, quantum communication, quantum key distribution. Okay, so the wavelengths can be different, and it depends upon, and at the moment, all this, if you want to design an experiment, where you want to generate entangled photons or single photons, this all the very less equipments are available in India, and most of them have to be imported. Okay, so again, which means that there is a lot of opportunities there as well. Now, let us talk about quantum gate. Okay, so now this is a clip again from a book on quantum information. It's a and communication with my PhD boss, Professor Anirban Pathak from JIIT. Now, what it says here, if it is not visible, then it says that Schrodinger's equation, it describes the evolution of the quantum state. So this is the state which I'm talking about. Xi, get xi is the Hamiltonian acts on it, and then I'm getting my state. Here, the requirement of real eigenvalues ensures the hermicity, H equal to H dagger of the Hamiltonian. And that in turn ensures unitary evolution of the state. Now, why am I talking here is because I'm now trying to relate the quantum information with the optics. Okay, so in the next slides, we will be using quantum optical gates. So now each gate has to have will have to ensure a unitary evolution. Okay, so which implies the blue lines which I have highlighted is of interest. So basically, a unitary transformation of a quantum state is a quantum gate. See, earlier I had shown you how a half-wave plate or a beam splitter or a half-wave plate particularly is used as a NOT gate. Now here I'm telling you that a unitary transformation of a quantum state is called a quantum gate. So now, thankfully also we had used the NOT gate as an example. So you can see the matrix 2 by 2. And I'm again sure I think this must have been covered. So this is just a recap. So whenever you have a NOT gate operator applied on state 0, then it becomes state 1. State 0 is represented by a column matrix, and this is how a state 1 is represented. Okay, so application of a NOT gate changes the state. There are other polygates as well, but let us now be very clear with at least one quantum gate, which is a quantum NOT gate. Okay, so a universe in the classical world, you have a NAND gate as a universal classical gate. In the quantum world, there are some there is a gate library which comprises of basic gates through which you can make any algorithm. You can actually use it for any algorithm. Now that comprise of a set of single qubit gates and a 2-qubit gate. So some operation which will take the qubit state anywhere around the block sphere. So you have seen how this operator, the quantum gates or the quantum operator looks like, and these are the quantum states. We will not go into the swapped gate or a CNOT gate. This is swapped gate is nothing but a combination of 3 CNOT gates, and CNOT gate has a controlled NOT operation. C stands for controlled. Now, this is important because in the next slide again, we will try to we have done some experiment on realizing a small prototype of a photonic quantum computer, and we are applying these single qubit gates. So, and you have the matrices here. Similarly, there are symbols also. H is represented by Hadamard, and this is a very interesting gate because this gives the superposition. So now, if I'm saying this gives the superposition, you would also, this is something like the beam splitter. So a beam splitter can be used to make a Hadamard gate. So you have a photon and you have the presence in 0 as well as in 1 state. So yeah, and these are phase operations. So this is a S phase gate, T gate. So basically, if you will be able to, we want to design or come up with an optical setup through which we can generate all the single qubit gates. Now, so here again, a computer scientist will be using the matrices, and an experimentalist will be trying to make the quantum gates, optical gadgets to represent or to do the operation which a NOT gate would be doing and satisfying the matrix. Some important gadget. So we discussed already the beam splitter. Now we'll talk about the polarization beam splitter. So the polarization beam splitter, it passes the horizontal and it reflects the vertical state. Okay, so in figure A again, you will be seeing that it is actually transmitting the H horizontally polarized light, and it is transmitting the V, which is the reflected light. Here again, something you must remember is H is 0, V is 1. This is path encoding. So when I'm sending a 0 state here, it is coming out in the transmitted path. And if I'm using a vertical state, it is getting reflected, or 1 is getting reflected. If I'm using two polarized lights of same nature, horizontal, we see that they are coming out through the two optical paths, output ports of the polarization beam splitter. Vertical, if I'm sending two vertical, again they're coming out. But if I'm sending different polarizations, then it is coming out through only one port. Okay, and similarly HV, it is coming out only one port but in a different path. Now, why this is interesting? Because we will be doing, you must have heard about entanglement purification or, Bell state testing. So all that will be using this kind of a setup. Okay, so this is how a polarization beam splitter looks like. And this is again from that book. Okay, so a polarization beam splitter and a beam splitter is looking similar from here, but once you do the, shine a polarized light, you will see it coming out only through one of the end. And of course, they will be marking also on top of it. Another very important optical gate is the half wave gate. So here, so this, again, a little bit of background. So this is a optically anisotropic material, which is known to be birefractive or birefringent. So here in single axis birefringent material, the incident ray will split into ordinary and extraordinary. The one which doesn't follow Snell's law is extraordinary, and the ordinary follows the Snell's law. Okay, and the incident ray will split the two rays into these O and E rays inside the material. And inside the material, they will be traveling with different velocities, okay, because they have different refractive indices. Now, this would imply that a single axis birefringent material, the refractive index for any is different from that of the refractive index of ordinary, which is NO. So now this property is explored in the fundamental experiments of computing and communication. It plays a very important role. These materials are made from quartz, which is birefringent, and quartz has different refractive indices for different polarized light, in different light polarized in different orientations. So when we, and another important thing is we should remember that if the refractive index of extraordinary is less than the ordinary, it is fast axis and the ordinary is slow axis. And if the refractive index of extraordinary is more than that of ordinary, then the extraordinary is the slow axis. Okay, so there will be some tricks to this trade, and so now coming to the application here, as you can see that the half wave plate is going to change the rotation of the light coming out from that system by 2 theta. If you are giving, if it is making theta with respect to its transmission axis, then at the output you are getting 2 theta. Now, why this is interesting? You can think of it as a NOT gate. If I'm giving the orientation at 22.5 at 45 degree, then my 0 degree horizontally polarized light will come out at 45 into 2, 90 degree, which is a vertically polarized light. So this is how the situation, is used or explored rather in computing. So I can be using it as a NOT gate. I can also be using it for say if I'm having a 22.5 degree at theta, then it will be 45 degrees. So I can create diagonal states also using this. Then we have a quarter wave plate. Now, quarter wave plate is also used to change the light from linearly polarized to circular or elliptically polarized light. So now I can have horizontal, vertical. I can have 45 degree, 135 degree. I can have right circular, left circular. Now, depending upon my application, for example, there are certain research works where the application is on the aerial platforms or drones. Okay, so now they will be they have used the right circular and left circular light. Right now, we are also exploring the linear polarizations. We are using diagonal states and linear polarized states, and we will be benchmarking the performance with them. So what I'm trying to say is, based upon the application, these states are chosen. So again, moving to the Jones matrices. So these are nothing, this is familiar with the classical world. And here I have represented the states, the 45 degree, minus 45 degree, the horizontal and the vertical states. So the polarization states are mentioned here, and the polarization vector. The corresponding Jones matrices, we just discussed the first two in the row, horizontal and vertical, ket 0, ket 1. Okay, and some remarks. So this again is available in that book. So this is nothing but a representation of state, again relating the optics with the quantum information. So here I'm trying to relate the device, linear polarizer, the quarter wave plate, half wave plates with the Jones matrices, and these are the measurement operators. So I really don't want. Okay, so this is some experiment which we have done with actually a group of interns had come, and they were building this web, a simulator where we suggested that you include only the single qubit gates, and they have built the circuit, and there's a Python code also which runs. So what we did was we have the optical plane. So the logical plane to optical plane connection was established. So that will be, of course, I mean, it has a lot of things in the communication, and in the compute part is also there. The quantum hardware part is there, which involves quantum state generation, characterization, and validation. So when I'm saying generation, I'm using the SPDC, which I had discussed in the earlier slide. Here is the laser. Here is the laser, which goes through the, through some optics and these optics are needed to purify this, the laser coming on it. And we also need to focus it and filter out the stray polarizations. Then we generate the daughter photons, the signal and the idler photons through this nonlinear crystal. And then we focus them back on the two detectors. Okay, so but here you will be questioning that you have a third beam splitter, so that is a tripartite or three-party coincidences. So there's an interesting experiment called the Grangier's single photon experiment, where we validate that photons are not divisible, and so this experiment which I had mentioned earlier, na? Yeah, this is the experiment which I'm talking about right now. And you can see this parameter, second order correlation function. And this is exactly the setup. There are 3 arms. This is called heralded detection. So what is heralded? That means I confirm the existence of 1 photon, that here I'm getting only 1 photon with a coincident event which is happening here on the other detector. So this is a heralded detection. And I'm using remember NOT gate I had mentioned. So I'm using a half-wave split as a NOT gate here. And you can see a polarization beam splitter and the 2 detectors here. So I think I've covered the important parts or the important optics which are used in any of the communication or computing experiment. Now, this is a small video. I want to show it with you. You will see that so there is a logical plane, and then there is there's a logical plane here where the student drags and drops the gates in the circuit builder. There is a code editor which executes the code. There's a simulator. You will see that the ideal case, the histogram shows all events are in. If I'm applying a identity gate, so if I apply identity on state 0, it is always an identity, right? So I will see 0 always. But when I'm doing a real-time experiment, you will see noise. And if the setup, see, the noise actually comes from the detector. So there should be minimal of about very, very low temperature. Yes, sir, I agree with you. So if you're talking about a temperature which is colder than outer space at 10 millikelvin, and that is where you will be talking about superconducting qubits. So artificial qubits. But in photonics, it's a room temperature. Okay, so yes, superconducting circuits, yes. So here I'm talking about photonics, which is room temperature. But of course, they are very sensitive to ambient light, noise, electronics noise, and heat. So we have to shield the experimental setup with against all this, which is entirely not possible. And also the detectors we work, okay, I don't want to. I start. Okay, I'll just hold it here. So I had shown you detectors in the optical setup. Detectors are only 60% efficient. That too depends upon the wavelength range. So I'm dealing with so many non-ideal components. You will see a noise, you will see a count in the other logic state, which is supposed to be 0. You will see counts there, and that is actually the noise. In Qiskit and all, you have noise mitigation techniques. So you have in the there are also some noise models, okay, but you have to map. So this is an open work, you need to map those noise models with the noise which is coming from this physical system. Now, let us look at it. So you see logic 0 getting maximum counts. Now I'm pulling. Okay, so now I'm putting a NOT gate, X gate in the circuit builder. The gate is dropped. You will see simulation result. I'm getting logic 1 state. You will see real time whenever the measurement completes. You will see most of the count in logic 1 and some counts in logic 0. 500 counts, yeah. It's 5,077, 779 in logic 1. So Hadamat, you have 0 and 1 both. 50% it is showing ideal in simulation, but in real time you will see counts in both the detectors, logic 0 and logic 1. So when the measurement completes, yes, it is completed, and you will see almost same counts, nearby counts, 5,900 and 5,600 in both the windows. So this is how, I hope if I'm closing this, I will not close. Yeah, cool. So now this is the experiment which I has just shown. So it is done all in real time. And you can see a lot of light here, but when the circuit is operational, madam, what are the applications? So I need to open the chat window. Yeah. What are the applications of single qubit based on optical communication? So the applications of, so qubit, if it is a communication, so communication means you have to use photons. Photons are known as flying qubits. And communication application is in quantum key distribution, sending anything secretly from one place to the other. And why that is important is, I will also talk about it in my next presentation. Because we do not have a classical solution of sending something securely. The problem is key distribution. There is no secure way of doing a key distribution from one part to the other part in any secure mechanism. Today, we use mathematical problems which can be solved in polynomial time using a quantum computer, something which is in billions of years, which it was predicted to be billions of years. With a quantum computer, it can be few seconds. So that is the reason application will lie in communication in terms of quantum secure communication. Other application would from quantum photo optics would be in sensing, metrology, and okay. Next question: because entangled photons involves in so much complexity. Sir, actually, since we are doing it for the first, I mean, for I would not say first time, because entangled photons, as you know, it has been I will also talk about it in my next slide. It is very old, but we are looking at this technology. It is compared to the classical computers, which is 70 years old, 70, 75 years old. This is just happening. So if we look at it, we will be able, we don't think that entangled photons is very complex. It's a simple process. You have a classical laser, it goes onto a crystal and it generates entangled photons, only 1 in billion. There are engineering challenges. But what we are trying to do is to simplify and to also write a book on that, so that if you follow those guidelines, it will be easier. I think not easy, I would say, but yeah, you will slowly get comfortable. Can we use single qubit based secure? Yes, single qubit based. Yes, of course. Can we generate entangled photons using Opti system? Opti system we have Opti system, and basically we use this for modeling the devices, like the modulators, the lasers, so it's not for generation of entangled photons, sir. So you can use a Qiskit, because this kind of has a single qubit representation. So you'll be able to generate entangled photons using an EPR circuit. You can use a Hadamard followed by a C0, and you can generate from 0, 0. You will be able to generate an entangled state, but it is not possible using an Opti system. Okay, so so now we go to the so maybe we can take a 5 minutes question answers. I think there are a lot many questions coming up. What should I do? I should stop presentation. Sharing your screen. Stop. Okay. Yes, sir. So I should see the chat window is. Single qubit can be generated using polarizers in opting system. No, it cannot be. And I said there is no further question after that, is it? CDAC is collaborating with Quera? Read an article that Quera is working in producing a large-scale quantum computer with 1,000 qubits. No, sir. CDAC is working on two things right now. They're establishing a reference facility in Bangalore with about say 80 to 180 qubits or so. I think I do not know the exact number. And it will be provided. The access will be provided to the nation. It will be from off-the-shelf components. So basically, to give you an hands-on on how a quantum computer. So we'll have a system installed in India in Bangalore. We have a quantum computer by QPi AI, which is in Bangalore. We have one quantum computer at ISC Bangalore. We have one quantum computer at TIFR, the first one with superconducting qubits. Then we have one in Kolkata with TCG Crest. Now, All these systems are basically from off the shelf, and so a superconducting quantum computer looks like you have a quantum chip at the end. Then you have the quantum chip in the dilution refrigerator. The dilution refrigerator actually has two parts, two technology levels. In the above technology, it takes the temperature from the room temperature to 4 Kelvin, and there is a millikelvin technology which takes it from millikelvin to 10 millikelvin, which is colder than the outer space. Okay, so and then after that you have control electronics, which is actually controlling these qubits sitting inside the dilution refrigerator. There is a room temperature control electronics. People are now shifting into cryo control electronics. So, and then you have the logical plane outside, the to transmit the gate you want to apply or manipulate on the superconducting qubit, which sits right down in the dilution refrigerator. So it's a technologically very complex. So people are looking at various options: topological qubit, ion trap. I do not know much about many different types of quantum hardware states, but actually we are also working. We are working on a project on building an Indian prototype of a quantum computer, superconducting based. So whatever I'm speaking comes from there, from the learnings from there. So it is quite complicated, sir. So people are still trying to understand which is a scalable method, scalable technique, which quantum, which type of qubit, whether it is superconducting or ion trap, will give us a scalable qubit. So 1,000 qubits are still noisy. And noisy qubits will not solve much of a purpose, and that is the reason you will not. We have not heard of any quantum advantage, and there are a lot of assumptions to whatever claims are being made in the quantum advantage. So that is the status, sir. But something which is very much is going to happen. We never know who is going to do it first. It is a matter of improvising the technology, and it's very interdisciplinary. You have a lot of classical algorithms as well. For example, the Willow one which came out, they had improvised on the error correction code. And for cracking any of the quantum problem, you will need millions of qubits. The coherence time is very less. It is in milliseconds, microseconds. So there are a lot of challenges to it. I suggest you should refer to the Davis and Co.'s five criteria for a quantum computer. So I don't think we are, world is still exploring, rather, I should say. So are there more questions, sir? I have a few slides only left. Chat window. Can I move forward or continue, madam? Okay. So I'll go back to sharing my screen. Okay, so now I'll again. So this window I will close it because I do not know. There is a little bit of bandwidth problem here. So, sir, I'm audible to everybody, right? I mean, there has been some instance with me where I kept on speaking and then later I realized it's not audible. Yes, madam. Okay. Okay. Thank you. So, yeah. So now we'll talk about the interferometer. Okay, interferometer. So the Albert, I forgot writing his name. He is Albert Michelson. He is the father of accurate measurement, measurement by means of interference of light. And this is called interferometry. So this interferometry, which I'm talking about, dates back to 1880 when it was built. Now, so this, as you can see here, that he has been awarded Nobel Prize in 1907 for the same. Now, the applications of interferometry is huge. It is there in the precision measurement, scientific research like gravitational waves, in quantum technology, in astronomy. Then there is engineering, medical, and biomedical. But what we would be talking about is its application in the quantum world. So we do use single photon interferometry. Now, interferometry, sir, please note everybody that this is actually a decoder. Whenever you are doing any quantum communication experiment or a quantum key distribution, what you have, which you will see in my next presentation, the quantum transmitter has a source and a quantum encoder. The receiver has a quantum decoder, a quantum measurement, and then you have analog to digital communication. So the decoder is actually an interferometer. So when I started working on quantum key distribution, which was in QNU labs, that was the time where I got, my hands on, on an interferometer. Of course, there are different types of interferometer. Today, we are talking about the construction and working principle, but there is so much advanced, types which we actually use in these quantum experiments. So single photon experiment, single photon interferometry, we use whenever we are trying to do Bell measurement related to phase encoding or decoding. We use it for the entanglement setup. QKD, definitely quantum communication, part of QKD. I mean, this is a measurement device in quantum communication experiments. Same goes for the sensing. So the interferometer plays a very, very important role. And that is the reason this chapter is included in the course. So it comprises of, so it comprises of the, why is it not moving? The beam splitter. So the figure here you can see is a beam splitter. Then you have a light source, which is after the beam splitter, it goes to either of the two mirrors, mirror 1 and mirror 2. Mirror 2 is the target mirror, and the first is the fixed reference mirror. So a coherent light gets divided into two beams at the beam splitter. One part is reflected at the fixed reference mirror, and the other hits the target mirror. Now, both the reflected beams are guided back into the beam splitter. The interference is generated by the superposition of both the beams coming from the transmitted and the reflected part. Now, based on the result of this interference, what happens is we get a sinusoidally modulated signal with periodicity half the wavelength of the coherence light. Now this is where you are seeing this ring-shaped pattern. Now we know in the physics, if you look at the optics part, whenever the constructive interference and destructive, but still I would like to mention this for the interest of everybody. So whenever the amplitude of interference signal is maximum, then we get constructive interference. And at that time, both the beams are in phase. You can see the bright lines. And destructive interference is when the amplitude of one interference is they're out of phase with each other, and at that time the signal is 0. So you can see here the white lines within the rings. So this is what we do from here is actually the change in the so the phase here information which I'm talking about here is encoded in the path difference. Again, very briefly, if the path length is 0, then it is constructive. There is no phase difference. And when the path length is not 0, then there is a phase difference and we get a destructive interference. Now, whenever I'm talking these simple rules of interference, it applies to daily line interferometer, Mach-Zehnder interferometer, Michelson interferometer, of course. The rules are the same, devices change. So this again is, this technique can be used in different applications in quantum communication. One such can be for the QKD, which I have repeatedly mentioned earlier. The intensities are used by a photon detector. Now, again, when we talk about detector, there are two kinds. One is where we are counting the number of photons, whether I'm getting 2 photons, 3 photons, and the other one is a single photon detector, which does not count, but actually it works in a very low intensity region, which is which is of the order of, say, it can take about, it gets saturated in about, say, some 2 lakh or 3 lakh kind of photons counts. So whenever I'm getting a photon is hitting the detector, I'm getting a TTL pulse, but that does not validate whether it's a single photons. It can be because of 1 or 2 photons or 2 or 3 photons. But had it been, if the mean photon number, actually we mentioned this with respect to average mean photon number, if it is more than 5, then there are chances of getting the detector burned. The detector is a silicon detector. They work in the Giger mode. So now again, see, the idea of this talk is to see how the physics relates to the quantum applications. So the experiment, the concept which I mentioned here, or the working principle, you know, it is it's you can see this is the quantum signature or the wave signature which I'm showing it here. So here what I want to say is, if you have electrons or photons, so here I'm considering electrons, they're coming out through the 2 slits. So this is basically this Young's double slit experiment as well, but how it relates to cryptography. So you have these 2 slits and there is an absorber, a sheet which absorbs the electrons. If I'm closing the slit 2, then I'm seeing a probability distribution curve, a bell curve, which is P1, because of the electrons coming from slit 1. If I'm closing slit 1 and opening slit 2, then I'm seeing a bell curve, again, P2, which is again probability distribution for the electrons coming and hitting the absorbent material from S2. Interestingly, if I'm treating these electrons as quantum entities, then it comes out, it has the wave particle nature, right? So it is coming out through both the slits together. Okay. And when it is showing this wave nature, I am able to see an interference pattern, P12. So this is the quantum signature, right? Now, if somebody is actually trying to see whether the electron has gone from slit 1 or slit 2, or remember the first slide I had shown you, if somebody is trying to see whether the photon has come into is either in the transmitted path or reflected path, something like that, okay? So if somebody is trying to see this, they are disturbing the state. We saw it is collapsing the state to either the one which from S1 or from S2. And that is the reason I'm seeing a bell state here as P12. So it's actually simple. You will see interference when nobody is observing, and you will not see an interference when somebody is observing. So let me just repeat. If nobody is observing the state, you will see the quantum signature or the interference pattern. But if somebody is observing the state, the interference pattern is destroyed. It collapses to a particle nature, and you will see a bell curve. So since I mentioned interferometer, and I told you earlier that in communication, particularly terrestrial over fiber, we use phase encoding, and the interferometers plays a very important role in as a quantum decoder in a quantum communication system. And I actually use this slide to tell how this wave particle duality, but here, since there was an interference pattern, I thought it will be a little, interesting to see how this forms part of the setup in quantum communication. So now we will move on to the microscope. So microscopes are optical instruments. They help us visualize with micrometer resolution. And it has several applications in medical. Let us not go into it, but yes, it has many applications in other science and technology sectors. And it has a lot of developments have happened in this area. A lot of improvisations and a lot of Nobel Prizes has been given to this subject. Now, as you can already see, it was first investigated by Robert Hooke using compound microscope. Then actually it is Dutch spectacle maker who is actually credited with one of the earliest compound microscopes. Nothing much, but just to see the significance. And so this particular area, this particular microscope, or any microscope will play a more major role in the quantum materials or in the materials section, right? Now, this is a simple construction it consists of two lenses, a metal tube, as you can see here, the product as well as the physics behind it. It consists of a metal tube with two convex lenses at the two ends. One is called the objective lens, and the other is the eyepiece. Now, both these lenses, if you see, they look almost same, but the cross section of the objective is less than that of the eyepiece. Okay, and the objective has a lesser focal length, short focal length, and the focal length of eyepiece is more than that of the objective. So now here, if you look again, the principal axis of the objective and lens and the eyepiece are on the same line. Now here, what we do is we have placed the object at between the FO and 2FO. Between FO and 2FO should lie somewhere around here. So it is placed in between that. And the objective lens can have, fine, we will come to that later. Maybe the magnification part we'll talk a little later. So so there's a principal axis is same, and it is possible to change the distance between the objective lens and the eyepiece. So in short, the summary would be, so if the object is to be observed, it is now illuminated here and placed in front of the object lens, slightly beyond the focal length of the objective lens, and it is the image is real and inverted, and an enlarged is formed because of this objective lens. Then the intermediated image lies within the focal length of the eyepiece. It serves as the object for the eyepiece, and the eyepiece is again works like a simple microscope. Simple microscope has one lens, my compound has two. So it works as a simple microscope, and we get an image which is virtual and highly enlarged and inverted with respect to the original object. Now, it can be formed at the minimum distance of distinct vision from the eyepiece. So in short, again, for people who are not from physics, in simple language, if the object, with an example, if the object is of say 1 centimeter length, it is, and the objective lens magnifies it 4 times. So the 1 centimeter will become 4 centimeter here, and the eyepiece gives say a magnification of twice. Then it becomes, the final object will become 8 centimeter. It becomes 8 times. So this is the simple formula, the magnification formula. The final net magnification is given by magnification of the objective lens multiplied by the magnification of the eyepiece. So in the course, we will now, since the book is under preparation, it was difficult for me to put out anything from the course here directly, but we will be investigating different experiments under this subject. So in diffraction, I would, there's nothing much to say here. We know that light travels in a straight line, but diffraction is deviation of waves from the straight line whenever it meets an obstacle and there is no change in the energy. Now, the name was coined by Francisco Maria Grimaldi, if I'm not wrong, please forgive, excuse me if the name is not correct, but in around 1660, so it was coined by him. So in a proper language, I would say the diffraction is a phenomena of light. The phenomena of light diffraction is actually the spreading of light into the geometrically shadow region when wave propagation is disturbed due to the presence of an obstacle. Now that can be an aperture or that can be a grating. Okay, so in this particular, whenever we are talking about this particular chapter or this particular idea in this in the book, it will be more about the diffraction, diffraction grating experiments like diffraction of light through gratings and things like that. We will be discussing the optical optical setup and how to conduct the experiment on that. So I don't want to get more into it, but to motivate you. I mean, this is something which we consider when I'm doing an aerial quantum communication, right? So when the single photons are traveling through the atmospheric turbulences, then dispersion and all these factors come into being. So it is, so this again phenomena is important from quantum communication perspective. So I think this is I'm almost, I will request your patience for some more time. So this is some, we know that the photon, Einstein had come out, it started in 1905 when he said that photon cannot be, is a discrete carrier of energy. 1901, right? 1901. And in 1935, the Einstein, Podolsky, and Rosen, they asked this question, that can quantum mechanical description of physical reality be complete? Now, why this happened? Because, okay, so fine, we all are celebrating 100 years of quantum mechanics, and I hope we know it's because of the paper by Heisenberg on matrix mechanics. So matrix mechanics was published in 1925. So from 1901, Einstein started becoming uncomfortable with the idea of quantum mechanics because of something called non-locality. So then he started questioning the fundamentals, the basis of quantum mechanics. So one such thing was the EPR paradox. And after that, what happened was in 1935, at the same time, Schrodinger's cat also became very famous. So Schrodinger actually is credited with coining the word entanglement, and he was talking about the wave function collapse, which again, so both these things with the EPR paradox and the Schrodinger's, which were the arguments formulated to prove the existence of quantum, became the heart of quantum mechanics. Okay. Now, what happens here after that is Bell. So after that, Bell studied this paper, this particular paper, and he became fascinated, and he's tried to prove whether classical, the classical world is actually, the quantum is actually compatible with the classical hidden variable theory or not. He tried to prove it is compatible, but then he found that the classical mechanics is compatible, but quantum mechanics violates that inequality. Okay, so this was a theoretical proof. Then Clauser had come, the Clauser had come, and he became fascinated with Bell's paper, and then he formulated CHSH inequality, which can be experimentally verified. And then Allen Aspect was, he has, then there was an experimental test conducted in around 1980s and 1981, where Allen Aspect had shown this, this is experimentally verified. And then Zeilinger was doing the quantum teleportation. He actually, so Zeilinger did the quantum teleportation experiment. So you see, and you can see the national significance of this with our Honorable Prime Minister photograph with Zeilinger. So the thing is, something started at 1935, and then we got the Bell inequality. It was verified theoretically, then it was verified experimentally, and then there was an applications like quantum teleportation also executed. Today, we do communication at thousands of kilometers. We do teleportations between Earth and space. So things have progressed. Now, to understand what is entanglement, there was one question which I missed out. To understand what is entanglement, I think we have shown the generation, we have discussed the generation in past. Now, let me just quickly come to this equation. So entanglement cannot be written as a separable state. Okay, its existence lies in the two particles together. So that's the reason I told you it is a special case of superposition. It behaves as one state. It has some correlations, like if you are getting H at one particle, then the other particle, which is in other galaxy, will also be H. If I'm getting V, okay, now okay, now something I must tell you. Now, suppose I have an entangled particle in one galaxy, and then I'm putting the second particle of the entangled state into other galaxy. Now, if upon measurement, I get a horizontal state, then I know that the other state will also be a horizontal. If I'm getting a vertical state, then the particle in the other galaxy will also be vertical. Now, what is interesting is the particle in the other galaxy, he does not know that I am measuring and I am getting an H or a V. So the question or the trouble which Einstein had was, how does the second particle in the other galaxy knows that I have got an H? Because I could also get V. It is a random, right? So I could have got H or a V. So how the other particle, which is in other galaxy, knowing what I have in this galaxy instantaneously? So that is that is what was making him uncomfortable. So now this is again, remember I told you how to generate okay, so do I have also shown a video, but okay, fine. So this is the entanglement setup. This is the laser, then it goes through a crystal and following the process of spontaneous parametric down conversion. We are getting type 2 using a BBO crystal. We are getting 2 daughter photons, and then we are detecting them using these 4 detectors, right? So, so this is a technique of generation, which I've already discussed, and I don't want to, discuss it again. But what is I'm very excited about is this Bell violation. So when Bell had given that inequality, he said that classical world will always be less than 2. Okay, but in the quantum world, it violates that inequality. The parameter I'm getting is more than 2, and it should be within 2√2, which is 2.8. So we were struggling with this experiment, and we could finally crack and improvise and also correct certain parts, and we are violating the Bell inequality by 2.67, which is a very good number. And these are very neat interference visibility curves also, which you are seeing for the different polarization states, which has the, and this is the entangled states, which is generated. Remember, I told you about 2 circles intersecting, and this is where I'll be taking these 2 points. So these 2 points are coming here, and the other one is coming here. Okay. So this is how they are being captured, and they are separated. The pump beam, remember I spoke about separation of the pump beam from the daughter photons, because it's only 1 in billion. So the purple line is my pump photon, and it is filtered out. So yes, this is, and since I have been dealing with these experiments, and I have already developed quantum devices. Well, when I'm saying I have quantum developed, I have only brought the experiment from theory to the experimental test bench. And of course, there were other technical product team, who were taking from the table to the product. And I was also validating the experiments which was done on the product to say that yes, it is quantum. So that was my contribution there. So once we generated the random numbers from the entangled photons in our lab, so these are certified random numbers. So you will see discussions on certification of quantum random numbers. So now, since we have generated this with this, there is a physics or maths mapping to the physics, so it can be certified. Now there are many other things also on it. If you want to scan, you will also get some random numbers in your mobile phones. We have generated, and we have put them in a bank. We also validated the numbers which we got using the standard suits, and we find that it is behaving almost, it's very good. Let me also tell you here, just for your information, that quantum random numbers is nothing new. It was there since a very long time, but that time you were using radioactive decay principle, okay, which uses timestamp mapping to generate random numbers. But you could only generate 5 to 6 random numbers per second. Can we do QRNG using programmable way but running on quantum backend? So quantum, it is interesting right now. I'm not able to say yes and no, because if it is, I have to see what is the quantum entropy. Here, for example, the quantum entropy is entanglement. Now, in other case, so we have actually shown you two ways of generating quantum random numbers. One is the entangled one based, and the other one is the path superposition. So I need to know the quantum entropy. Then once you generate the state, if you're using it as a seed to buffer it up, then that is also one of the cases which people in this in the industry are also using. So maybe we need to discuss that problem, sir, when you are saying that you're using a programmable. So anything, any algorithm you are applying, it should not be done, because the reason of getting quantum random numbers from an optical source is that you will get them in megabits or in gigabits. So there is no need to buffer. You will be actually getting the numbers from the source. So I'm finally winding up, and I started this quantum education course and across all the 12 centers in CDAC. It started with introducing the basics, then the quantum circuits, and then the communication concepts, basic algorithms, and the advanced ones, which involves hybrid algorithm and hybrid architecture. Then we have hardware technologies like ion trap, superconducting, photonic, and finally hands-on the simulation. So the course is taken by the experts with whom I have learned, and I wanted to learn, or my collaborators. And my team is also giving the hands-on session, is helping on this aspect. We also have, oh, the voice is breaking. Okay, so maybe I should, so there's nothing much, so I will close and we'll have this discussion for 5 minutes. So the course was designed keeping all these 4 verticals. And I hope you are aware of this. Dr. Pillai is actually doing a fantastic job. So I hope you all are familiar with the course structure. What I find interesting is basically the lab manual, because unlike any other discipline, it has a flavor of optics, digital circuits, RLC circuits, radio frequency technology, data acquisition, interfacing instruments. So because since I have dealt with, bringing out system from TRL2 to TRL5 or 6, I see that this is also a very important part. And of course, quantum simulations. Also, if you want to contribute to quantum, it is not very important that you have to understand the entire field. Even if you are very good in any of the technologies, there is a way to okay. So for QRNG, is Hadamard construct good enough? Yeah. So if you are generating, say, suppose in Qiskit, you generate a Hadamard gate, give a 0, initialize to 0, then Hadamard gate, then you have 0 and 1, do measurement. But it gives you an average number. So I do not know how you are going to correct it, but yes, it is one way. Yeah, and this is my team. Thanks to the team, because most of the time they are doing the hard work. So now I think I will end this, and I would like to take some questions. It's fine. Yes, sir. There's a chat window. So I think, how far is it? Okay, so the last question is, there was a recent news China has proven entanglement with a distance of Earth to space. How far is the real claim? See, China is advanced in this area. They have done, they're a lot advanced. So if they are saying something, I would not say yes, but I think, but this is possible, because entanglement generation distribution has already been done by many different scientific groups all around the world. So no need to say it is something which is which cannot be done. It is very much possible, and it is. I think if they are saying, then we should wait for their research papers. Call for proposal. Call for proposal for quantum lab is not yet available. It will be announced soon by NQM. It will be announced soon. Can the single photon be simultaneously in the reflected path as well as it? Yes, sir. That is the reason I was putting so much of time there. It is actually in both the paths, but when you are trying to detect it, it is collapsing either to us in the reflected detector or in the transmitted detector. So it's a wave function collapse particularly, and it is actually existing in both the paths simultaneously. Now, I know it is, you'll be curious, but if you do an interferometer, if you add another beam splitter and you allow the two paths to merge and interfere, it will be giving you a constructive interference. So that means that it is actually in both the paths. Thank you, sir. We want to set up a quantum lab. Yeah, for sure. I mean, we can discuss. At the same time, this is a very advanced lab. So now, since I have done things from ground, so I was also working at Bose Institute, where you need under a theoretical physicist. But now I'm working with a funding of an experimentalist, so I could get the advanced detectors, advanced systems, and the life is so simpler that I can generate things within few weeks or a few days, which used to be months. So if you want to have a quantum lab, that's very good. I'll try to help, but again, we have to remember that part. Dr. Pillai, nice to see you. Now it looks like, I mean, it's a otherwise it's speaking to oneself. Yeah.
Right.
Yes, sir.
Yeah, but the interaction that goes on in the chat is good, so that at least it keeps us alive, keeps your TK. Somebody's there listening to it. So, yeah, thank you so much, ma'am. Any other questions, please, quickly, because ma'am also may have some meetings
How
lined up.
is teleportation possible with photons? Teleportation is a communication protocol. It involves sharing of entangled state at both the parties, and then you have an arbitrary qubit interacting with one of the belt state, and then you do a measurement on the other. Then you will retrieve the state. The arbitrary state does not exist anywhere in between. So teleportation is a communication protocol, and therefore you have to have photons. So at the same time, it is also a part of the quantum computing network. So when you're talking about distributed quantum computing, it will be a part of that as well.
Yeah, regarding the lab, some of you have been asking. So I've been also discussing with ma'am, and it involves a little bit of electronics lab. A part of it is electrical lab, and a part of it is physics lab. So I'm also trying to put up a list of equipment that you can procure. I'll take the help of Dr. Anindita as well, and we will share with you. You can then have to contact the vendors and work out your solutions, right? So estimated cost also we'll let you know. Tentatively we can, but we cannot estimate the market prices. So that is how it is. Yeah. Ma'am, another question. Yeah.
Yeah, for teleportation, photons are being used, sir. Yes, only photons, because you need to share the entangled state. But again, I would say, because it's such a developing technology, if you have many circuit lines, and you want to send a quantum state from one circuit line to some other circuit line, you may want to do a quantum teleportation. So then again, it depends upon the nature of quantum hardware. It will be a very important part of the distributed quantum computing network. So you can also submodules. So it is something which I would say, yes, people have done it using photons, using polarization encoding techniques, but it will be a part of distributed quantum computing as well. Is it possible? Yeah, sure, sir. Please do come CDAC Pune. We'll be happy to show you our lab and the experiments we are doing.
Yeah, there are possibilities for internship also. They will advertise from time to time. Project start.
Yes. Internship is quite flexible. You can apply, I think, whenever you that time comes. So we'll be happy to support you there. Thank you. So
how many maximum qubits for teleportation? Yeah, maybe the last question.
So for teleporting one quantum state, you need one bell pair. So if you, it depends upon the number of how many states you want to teleport. Same number of bell pair has to be given. There is no limit, I mean, as such. Yeah.
Yeah, you can look up ma'am on LinkedIn and CDAC profile, so you can get that. So CDAC Pune. We'll share ma'am slides also, whatever has been delivered.
Yeah. So I'm sharing my profile also here, sir. I think that should be.
Yeah, sure. Yeah, you can put it on the chat.
That also, yeah.
So we are very happy that we could have Dr. Anindita because of course she adjusted. I was very doubtful. She was requesting me to postpone it. Already we are postponing Dr. Santosh's lecture. So that was what I was little worried. We were making a lot of changes. So anyway, that she could make it today, and we are happy that you have got. And of course, she'll be discussing a lot of challenges and also some of the research work that is currently going on in CDAC on 6th also. 5th, we will be having lectures by, I think Dr. Santosh may not be available on 8th also. So we'll wind up our class on 6th. On 5th, we will conclude with that. So, tomorrow we'll have a normal class starting at 2 o'clock. I'll let you know either Dr. Jaykumar or or Miss Janani will be taking the lecture on 6th. Dr. Anindita will come back to us again. So that's where you can conclude. So thank you so much, ma'am, once again for being with us, sparing your valuable time. And thank you all. So we'll meet at 2 o'clock tomorrow. Thank you so much. Thank you. Yeah, you can, Radhakrishna, you can close. Thank you.